So in the last video, we just started discussing the details of dispersion, and we ended with a table that looks like this. And what we discussed is that the index of refraction, which is always given the symbol n for materials, is not absolutely a constant. In fact, the index of refraction depends on what wavelength you're talking about. And as we discussed in the table here, all of the indices of refraction for blue light are going to be the largest. And all of the indices of refraction for red light are going to be the smallest. That's just across the board, and of course the green sits there right in between. The general rule that we have then is that the index of refraction is sort of proportional to 1 over the wavelength that we're talking about. There's a bit of an inverse dependence in there. It's not hard and fixed, but approximately is just fine. And so what that means for us in terms of dispersion is as follows here. Snell's law has sort of an implicit dependence on this thing, because Snell's law says that n1 times theta 1 is equal to n2 times theta 2. And these angles that we're talking about, remember, are for refraction. So here comes a light ray, and it goes in like this, something like this, something like this. This angle in here would be theta 1, and this refracted angle in here would be theta 2. And so what you can see is that the refracted angle here, if you just do a bit of simple algebra here, is n1 over n2 times theta 1. And so we discussed this in a previous lecture, but you can see from this equation here that the refracted angle depends on the ingoing angle for sure. So theta 2 does depend on theta 1. But there also is some dependencies here on the indices of refraction. And if these indices of refraction here depend on wavelength, then the outgoing angle is going to depend on the wavelength too. And that's the really sort of hidden implicit thing in Snell's law that we haven't discussed to the point here, is really it boils down to is that theta 2 will depend on the wavelength for sure. Theta 2 will depend on the wavelength. And of course the meaning of what theta 2 is here, theta 2 is the refracted angle. So the refracted angle will depend on the wavelength. Can we come up with a simple rule then that tells us what the dependence is going to look like? Well, as you recall from the table here, blue light always has the higher indices of refraction. So if you look back over here and you see that the index of refraction is related to the two angles, so the refracted angle depends on the wavelength, well, the simple thing to remember about this then is that really blue will bend, and remember refraction is our bending law, more than green or red. So blue will bend more than green or red. And I'm just getting that right from the table over here. If you have a wavelength that has the higher indices of refraction, what that's going to mean for you then is that all the refraction at this wavelength here is going to result in the most bending. Over here, this is going to result in the least bending. And the green, of course, in the middle here will sort of be mid-bending, something like that. So green won't be the most or won't be the least. It'll be somewhere in between. But blue is definitely going to bend the most. Red is going to depend the least. So this dependence on the index of refraction, this relationship right here, allows us now sort of to understand how the prism works. So the prism is going to work like this. Let's draw it one more time, and then we'll sort of walk through the logic here. Here's the prism, and here comes some white light into the prism like this. Okay, here comes some light in. And let's think very carefully about what we said. We said that blue bends more, or the most even. So we can't see the blue in this white beam, but we know it's in there because white light is composed of all of the colors. So we know there's some blue in there. So here's a little bit of blue. I'll just pretend like I'm able to pick that out of the white light. And so what will happen is we say, well, that's going to bend more. It's going to bend down like this. And why does it bend more? Because this blue here has the highest index of refraction. Okay, red is going to bend the least. And so the red is sort of in this white beam too, and it's going to hit the prism. It's going to bend the least. So I just won't bend it going very much like that. And why is that? Because red has the lowest N. Go back and look at the table. You can see for glass, red has the lowest index of refraction. What about the green? Well, the green's in this white beam too, so it's going to sort of hit the prism, and here comes the green out like that, because again, green has the mid sort of N relative to the blue and the red. So that essentially explains the prism effect, but instead of saying a prism effect, which sounds kind of amateur here, let's just say that all of this is exactly what dispersion is. So what we're going to call dispersion then is separation of colors, and in technical parlance it'll be or wavelengths. I'll say or wavelengths, separation of colors or wavelengths due to their color. And if I want to be maybe a little sort of more abstract about it, I can say separation of, instead of colors here, maybe on the onset right here, instead of colors, maybe I'll even use the word light. Separation of light due to their color. And I'll modify it even more now. Instead of saying there, maybe I'll say it's. So that's what dispersion is. It's separation of light due to its color. And the separation is exactly what you see in this diagram up here, which we can call, if you want, you can think about as the prism effect. And I'll call it the prism effect because I think most people are familiar with this picture here of white light going into a prism and seeing the rainbow up there, but it's not really called the prism effect. When you see this separation here of light according to its color, that's what dispersion is here, separation of light due to its color. And of course, the reason for dispersion is that N depends on what? Depends on lambda, the wavelength. That's the reason we get dispersion. Okay, so in the next couple of videos, we'll wrap some things up on the questions that we have. In particular, we'll talk about why we see rainbows and something called the green flash.